Okay, so as an introduction to enzyme kinetics, we want to refresh your memory on reaction energy diagrams. So this is a topic that you have seen in general chemistry, and we want to make sure that we refresh your memory here and also kind of take it a step beyond possibly for what you talked about then, and really put it in context of what we're trying to accomplish here. So obviously this is a reaction energy diagram. We're plotting free energy here as delta G versus a reaction coordinate, the progress of the reaction. In this case, the relative energies of the reactants over here and the products over here are exactly equal. So the relative positions here determine the position of the equilibrium, the position of the reaction at equilibrium. So here, since reactants and products are exactly equal, we would expect to have the same amount of reactants as products at equilibrium. Okay, we're just as likely to go from reactants on the left-hand side here up over this big mountain to products over here as we are to start from products, go up over the mountain and back down to reactants. Okay, so it's only the position of the reactants and products that determine the position of the reaction at equilibrium. And as we said here, we'd expect a 50-50 mixture because the reactants and products have equal energies. Okay, but alone, the products of the reactants, the energy of the reactants and the products, tell us nothing about how long it'll take to reach equilibrium. Okay? So the transition state is the molecular tipping point between the reactants and the products. And this is a transient species. It exists for a single molecular vibration. It's not stable. It's not isolatable. So we're talking about the very tippy top of this mountain here. Okay. If you tip this way, you go back to reactants. If you tip back the other way, you go to products. Okay. So this is the transition state energy right here. And the difference between reactants in the transition state or products in the transition state is the activation energy barrier going from reactants to products, reactants in transition state here, or products to reactants between the products and the transition state here. So the difference in these energies is the activation energy barrier. Okay, and this is what's going to determine how fast we reach the equilibrium for that reaction. So this is the barrier. In this case, for this reaction where we have reactants and products with exactly equal energy, then the activation energy barrier for the forward reaction is exactly the same as the activation energy barrier for the reverse reaction. So just like the positions, the relative energies of the reactants and products tell us something about the position of the reaction at equilibrium. And they don't tell us anything about how fast we get there. The activation energy barrier tells us how fast we get there, but doesn't tell us anything about the position of our reaction at equilibrium. Okay, so one characteristic tells us one thing, and the other tells us the other important factor, and only together do they tell us what's going on with that reaction. So the greater the activation energy barrier is, the longer it takes for our reaction to reach an equilibrium. Okay, here we've got a relatively high activation energy barrier. We'd expect this reaction to be relatively slow. However, in this purple reaction, we're starting with the same reactants and the same products, but we're taking a different path here, which means that we have a much higher transition state energy, which means we have a much higher activation energy barrier. Okay, we've decided to go over a different part of the mountain range, and we have a taller peak to climb. In this case, we found a shorter mountain, a different route, lower activation energy barrier. Okay, so we have a lower barrier to overcome in both the forward reaction, converting reactants to products, and products to reactants. So both of these reactions, the forward reaction and the reverse reaction, are going to be much faster. Takes less energy to get over that mountain, so we'll get to equilibrium much faster. But it doesn't change the energy of the reactants or the energy of the products. So it doesn't change the relative amounts of these. We'd still expect 50-50 in this reaction. Okay, so here we've got a different reaction. This is an exothermic reaction. We're losing energy to the environment. We're losing heat here because reactants are higher in energy than products. So this overall decrease in energy tells us that our reaction is going to be going from reactants to products. At equilibrium, we're going to have more products than reactants. Okay. Well, now we have two different activation energy barriers here. We still have the same transition state. In this case, we have a single transition state. We don't always have to have a single transition state. Every time we have a mountain peak here, that's a transition state. And anytime we have a little valley, that's an intermediate. Okay? So any little valley is an intermediate, any transition state is a mountaintop. So here we've got a reactant going to product through a single transition state. We have a single activation energy barrier going from reactants to products. That's here to here. Okay? So this forward activation energy barrier is lower than the reverse activation energy barrier. This is the energy barrier going from reactants to products. Going from products to reactants, we have a much bigger barrier. Okay? We have to go all the way up this mountain. So once reactants fall down into products, it's less likely that a product is going to climb all the way back up this mountain and revert into reactants. That's why you get less reactants, more products at equilibrium here. Okay, so here are two reactions. Sorry, one reaction, two different paths, right? Same reactants, same products, same energy for both starting out. The black trace has a higher activation energy barrier. It's going to be a slower reaction. The purple has a lower activation energy barrier, lower transition state energy, so it's going to reach equilibrium faster. Again, both exothermic reactions, and again you should be thinking in your mind now what an endothermic reaction is going to look like here. Products are going to be higher than reactants, and reactants are going to be favored at equilibrium. So when you add a catalyst to a reaction, you're basically going from the black line to the purple line here. We don't change the energies of the reactants or the products. They're exactly the same. But what we're doing is stabilizing the transition state. We're lowering this energy of the transition state. And we do that in the enzyme active site. So we're effectively lowering the activation energy barrier. Now we're lowering this activation energy barrier from here, right? This difference down to this difference. We're lowering that activation energy barrier for the forward reaction. We're also lowering it for the reverse reaction. That's why we don't change the relative amounts of products and reactants at equilibrium. So here's our uncatalyzed transition state energy up here. Activation energy barrier for the forward reaction. And here's our catalyzed transition state with our activation energy barrier here lower. Okay?